Thanks very much for coming back. And so in the next session, we have that's unfortunate choice of words, but you're all captive, so you have to come back. So the next session, first off, we have Andrew, who's going to talk about some of the his work on the flow of fluidized particles.
Okay, thanks very much. So yes, I'm Andrew Hogg, and I'm going to say something about the flow of fluidized particles. This work is with Mark Gilbertson, who is in the audience. Mark's there. And with a student we've had, David Jessup. And David's the one on the right. And we hope that David is submitting his thesis today. So we're pleased to talk about his work. And in some ways, it's very appropriate that we should speak here, because this is a project which kind of arose in the Newton program 5 years ago. That's when Mark and I first started talking about these things. And of course, the project turned out to be much more complicated than we had first anticipated. Anyway, so just by way of introduction, of course, some of this everyone will know, but I'm just trying to make sure we're starting from the same point. We say that granular materials are fluidized when their weight is borne by the interstitial fluid. So this is going to be a talk where we've got granular materials and we're concerned about the fluid that surrounds them. And the key feature, or the key feature we're going to be concerned about today, is that when fluidized, the mobility of the material is greatly enhanced. So here's an industrial application. This is known as the Dyna slide. And here's a picture of it. And essentially, you pour in granular material at this end, and out it comes at this end, and air is pumped in through here and distributed through this base plate. And it means that you can pour granular materials down a slide which is at an angle much less than the angle of repose. So essentially, we've increased their mobility. And the company that sell these things sell them in various sizes up to 10 meters or so, and they're used for connecting hoppers together in industrial processing. A second application is a geophysical one. And here's a volcanic flow. And in volcanic flows, you've got the particles, but you've got also lots of gas. And what we're interested in is how the presence of the gas can greatly enhance the mobility of these types of flows. And of course, we need to know about that for hazard assessment and other geophysical problems. So again, this is rather an introduction to fluidization. But what we're going to have is some particles, and these are this kind of gray matter here, and we're going to pass a gas flow from below through a porous plate. So in dark grey, we have this porous plate, and we're forcing a gas flow from below. And when we pass the gas at a sufficient rate, we manage to balance the weight of the particles. So the gas flow exerts a drag on the particles, which supports the weight. And this happens at a critical gas speed, which we denote UMF, the minimum fluidization velocity, or the minimum speed with which the gas has to flow to support the particles. And here I've actually shown little pockets of gas. And that's because many of these systems, when fluidized, actually go into a bubbling state. And so you actually get bubbles of gas passing through. We won't concern ourselves with that too much in this talk. And if you measure the pressure drop across the bed, from below the porous plate to above the particles, what you find is that the pressure drop increases with flow rate, and when you become fluidized, the pressure drop then remains constant. And it's because, at that stage, you've supported the weight of the overlying grains. So they're fluidized. OK, here's our experiments. Essentially, our configuration is almost the same as the Dyna slide. So what we're going to have is a thin channel, which we can incline at some angle. And we're going to have a porous plate through which we're going to pass gas flow. And then we're going to release particles at some constant rate at one end. And what we're interested in is the rate at which they spread down the slope. Okay. The channel is quite narrow, a centimeter or so wide. The walls are made on one side of metal and on the other side of glass. I'll show you a photo of the channel in due course. And it's a meter long. And we take whatever measurements we can, which is mainly with video equipment. So we video from one side, and we measure the profile of the intruding current, and we try and do some PIV to get velocity profiles. And I'll show you data like that. Let me tell you about the particles. We're using glass ballatini, 350 micron. They've got a density of 2.5. And for those of you that know about these things, they're Geldot class B. our particle Reynolds number. So this comes out to be about order 1. This is basing it on the gas speed. So it means that the interaction between the gas flow and the particles is essentially intermediate between viscous and inertial. The Stokes number, which measures how the particle itself responds to changes in the gas speed, is rather larger. So essentially, these particles don't follow the gas speed particularly well. They find it hard to, if the gas turns a corner, the particles tend to go in a straight line. That's the way of thinking about what the Stokes number is telling us. So these are a quite high Stokes number. Okay, I'm going to show you a movie, and in this movie, we're going to be pouring in particles at one end, and then at some stage, we're going to turn on the gas flow, so you actually see the increase in mobility. So all being well. Okay, so here we are. We're raining in particles at this end, and of course, we're inclined at about 15 degrees or so, and we're building a wedge, which is essentially at the angle of repose, building a sandcastle. At some point, we're going to turn on the gas flow, and now we're going to turn on the gas flow, and the gas is injected into this chamber, and you see the mobility dramatically increases. We're still raining in particles all the time here. I haven't turned the source off, and so we're getting a very thin flow, which is flowing along the bottom. At the end, we've got a suction device, and so we're removing particles. And so in the end, we're going to end up in a state where we have a very thin but fairly constant thickness of flow along the bottom. You can see the flow speeds. Well, you can see this is raining down here, and the flow speeds are tens of centimeters a second or so. And we may just get to the steady state. Here we are. So now the flow is rather thin. It's perhaps a centimeter thick or so, and we're in a really pretty steady state. The flow is still going at this stage, right? It's just very thin. Okay. And our apparatus, we've got a glass front plate. The back plate is metal, which we've painted black at the lower half to help with visualization. Okay. So now what I want to show is a particular experiment, and this time we're at 14 degrees and we're raining particles in at this flux rate, 9.4 centimeter cube per second. And this is in close-up. So we put the camera really close to the plane. So now we see this steady state. This is about a centimeter thick. You can see a rather diffuse layer at the top. And you can see that it's not quite steady. There are minor oscillations, but perhaps they're rather minor compared to the overall thickness. And this doesn't seem to be playing particularly well. This is a slow view of the front coming through, and I want to show this to convince you that it gets into this steady configuration rather rapidly. The front goes through, and then we're left with a fairly constant layer which flows behind it. So we do hit this steady state. Okay, so the flows develop fully developed steady state, and by varying the channel inclination and the flux rate, we could think of using this experiment as a rheometer to try and determine relationships between bulk properties. Okay, so in particular, we could measure the flow depth as a function of the flux and of the angle. Those are the things which we can experimentally control. And here's some data. So what I'm plotting here is the front position as a function of time on log scales for various different fluxes and for various different angles. And the point I'm trying to make here is that even the front is moving at a constant speed. So you can see these various data series, and these thin gray lines are of gradient 1, showing that the front position is proportional to time. Okay, so we're reaching a steady state where everything is flowing at a constant velocity with a constant height. That's not true if there's no slope. So if we put the bed horizontally, we can still perform the experiment, but now we find that the front position essentially goes like time to the 2/3 power. So again, here's many data series. The color coding is essentially telling you the flux rate, log time, log position, and this is a 3/2 bar. So you can see that essentially the front position is varying like time to the 2/3. So what we'd like to do, of course, is to have some theoretical framework for explaining these observations. Can we predict the flow height? Can we predict this flow scaling? The velocity profiles. So these were determined using PIV techniques with a high-speed camera. So we focus the camera on the particles closest to the glass wall and track individual structures, and we find these types of velocity profiles. So in the first plot, we're seeing the downslope velocity against depth, and the different color series are for different fluxes. And then in the second plot, I've scaled the downstroke velocity by the maximum, and I've scaled the flow depth by the particle size. So we're seeing three key features. We're seeing a slip velocity. They're not going to zero velocity at the base. We're seeing some kind of shearing zone, which is perhaps 15 particles wide or so. And then we're seeing some plug-like zone where there's less shear. Okay. And these are results for both 10 and 15 degrees, but we find this generically. In fact, we also find the same velocity profiles when it's flowing over a horizontal surface. Okay. We also try and measure what's the horizontal gas speed. Well, of course, that's rather more difficult to measure, but you could think about tracking bubbles which are advected along, and we did that. And you could think about puffing in very fine particles and seeing how they move horizontally. And essentially, we come to the conclusion that the horizontal gas speed is about the same as the solids. When I say horizontal, I mean parallel with the bed. So horizontal could be downslope slightly, and vertical is normal to the bed. So here's some bulk results. Let's look at the rightmost one first. So this is flow depth in centimeters as a function of inclination angle. And the three different colors are essentially for different input fluxes. Although these are nominal fluxes because we actually have to recalibrate the delivery device after each experiment, but notionally they're the same. So the general behavior we're seeing is that let's follow this green dashed line, as you go to steeper angles, you get thinner flows. Let's look at this pattern over here. Now we're putting the flux rate, the flow depth as a function of flux rate, h as a function of q, for various different angles. And the different color series represent 12 degrees up to 26 degrees. And what we see is that there's some region where flow depth h varies linearly with q, and then as q increases, it tends to roll over. And there is some systematic ordering here. As you go through the data from the top to the bottom, that corresponds to increasing angle. So increasing angle gets you to roll over faster. Okay, so those are the types of properties we'd like to be able to explain. Okay, so now I'm going to describe what we've tried to do in terms of a theoretical formulation. And to be quite honest, we're a bit stuck. But you'll see how far we've got. Okay, so the first thing is we need to say something about the drag between the particles and the gas, because that's a key feature. That's actually keeping the particles supported, keeping them fluidized, if you like. And what we're going to use is a two-phase model, and we're going to write down expressions for mass and momentum conservation, and possibly energy conservation for each phase. We're going to assume that once fluidized, the volume fraction of particles remains more or less constant, or the voidage, which is the volume fraction of voids. And this is repeating what I've said, that the key dynamical feature is the interaction between the solid and gas phases. Well, one way of capturing that, which has been used for several years, is an empirical expression known as the Ergun equation, which gives you the drag force between the solid and gaseous phases. So U here is the gas velocity, V is the particle velocity, mu f is the dynamic viscosity of the gas, d is particle side, epsilon is voidage, rho f is density of fluid. So essentially, this is a drag law with a linear term and a quadratic term in velocity difference. And so you could think of this being essentially drag due to viscous processes and this due to inertial processes. And the regime we're in, we're all dominated by this first term. So essentially, the interaction between the gas and the solids is dominated by linear drag law, linear in velocity difference. Okay. Well, now we want to try and calculate a fully developed flow. So a flow where the particle velocity only depends on height off the boundary, and the gas velocity depends on height off the boundary, and in the vertical direction or in the normal direction to the boundary we have some constant gas speed. So let's look at the vertical momentum balances first of all. For the fluid particles, we have the weight of the fluid, a pressure gradient, and the vertical component of an interaction term. For the solid, we have the weight of the solids, the divergence of a normal stress, solid stress, and the negative, or the negative of the interaction law. So when we add the two together, the drag between the two cancels out. Okay, and what is the law for this interaction between the fluid and the solid? Well, following arguments by Jackson, it corresponds to something to do with the fluid pressure gradient and something to do with the drag term from the Ergun equation. So if we add the two equations together, we get a normal force balance, which essentially says that the total normal pressure, or pressure plus solids contribution, is essentially hydrostatic. And in a fluidized state, essentially, sigma zz, the solid's normal shear stress, the solid's normal stress is 0, or vanishingly small. So it's all supported by what's happening in the fluid pressure. So it's a bit like having hydrostatic pressure. And then we could use the drag law to determine what the gas speed, flow speed is. Okay, now let's look at the horizontal momentum. So this is for the fluid phase. We pick up this inertial term because remember the gas speed has a component normal to the boundary. So that's basically saying that gas is lost out the top, and that carries with it some inertia. The weight of the fluid, the interaction term, I've just taken a linear relationship on velocity difference, and fluid shear stress. And then for the particles, we have no inertia in the fully developed state, the particle weight, the interaction term, and a solid's shear stress. Now then, when we try and estimate how large the terms must be, we find that we can only get balance in this equation by assuming that this solid shear stress plays a non-negligible role. And the easiest way to see that is if you add these two equations together, then the drag term cancels out. And so all we're left with is inertia, inertia of the fluid, total bulk weight, and the divergence of the two shear stresses. And the fluid shear stress isn't large enough to balance those other terms. Okay. So how large does this fluid shear stress, this particle solid shear stress have to be? Well, just in order of magnitude, it has to be rho SGH. So that looks like a Coulomb expression, but of course we can't use Coulomb because there is no normal force carried by the solid state. So we can't use a regular Coulomb closure. So this has been the puzzle. And if you think a bit harder, because there's a slip layer at the bottom, we do find that this there's a basal boundary layer where the fluid shear stress comes in, but we'll see that illustrated in due course. And so we need a rheology for this fluidized material. So here's one suggestion Hogg and Sangani 10 years ago made. And it's based on the observation that actually the Stokes number for these particles is quite high. We estimate it to be about 1,000. So it means that actually we should expect the particles to collide into each other. They're very inertial, they're like banging into each other. Okay, so this is essentially trying to summarize the Hogg and Sangani argument. So the presence of a gas flow provides an additional source of agitation to the system. So if you just have a dry granular flow down a slope, you produce agitation by what's known as shear work, essentially the product of the shear stress and the velocity gradient. But the presence of the gas flow provides an additional way of generating agitation. And their argument goes like this, that essentially you get perturbations to the configuration of the system, and it's the viscous response to these perturbations which generates the additional agitation. And through some rather complicated calculations, they show that it's actually due to the autocorrelation of the viscous force felt by a particle. So we can estimate what that is. So the viscous force would be the viscosity times the particle size times the velocity. A correlation time is the particle size divided by the square root of the granular temperature. And so we can find the energy source must scale in this way. And then also the shear stress, as in other kinetic theories, goes like the particle size times the granular temperature square rooted times the velocity gradient. So essentially, this is a way of suggesting a rheology for this system, in that we've ended up with something which is akin to a solid phase viscosity. I don't like using that term, but essentially we end up with shear stresses which are proportional to a velocity gradient. Okay, so let's try and illustrate whether we can get flow profiles which are reasonable with this. So I go into dimensionless variables here, scaling the flow depth by h and the flow velocity by a scale which comes out of the drag term. And what are we left with? In the fluid phase, we have, this is essentially measuring how large is the fluid inertia. And that's tiny. And it's tiny because rho f over rho s is tiny, 1 in 1,000, and d over h squared is tiny. So that really is a very small contribution. We then have the downslope term, an interphase drag, and a viscous shear stress. And then in the solid phase, we have the gravitational term, the drag term, some measure of how large our solid's viscosity is, if you're going to allow me to use that term, and then the second gradient. And if you solve these two equations, you get flow profiles like this. Now you need good eyes, but there's a red curve and a green curve, and the green curve I put in some arbitrary slip velocity at the bottom, and you can see there's a little boundary layer where the red and the green are different, so the fluid and the solids are moving with different horizontal speeds, but in the bulk they're moving with the same speed. And we're getting profiles where there's some shear at the bottom and the shear decreases with height. So this has the right type of character for what we were seeing in our PIV measurements. Of course, there's lots of things we don't know, but there is some hope that this is reproducing what we've seen. Now let's see, what does it tell us about the flux, the Q versus H. Flux or H versus Q. The H is a function of the height as a function of volume flux. So the formulation leads to a term which is due to a slip velocity, and then a cubic term. And so if I plot H against Q, and if I increase the angle, I should expect the curves to roll over sooner. And if I plot H as a function of sine theta, and I increase Q, I get the curves should stack up on top of each other. And of course, that's the character of what we have in our observations. So I can't make a quantitative comparison, but at least there's some qualitative consistency between these ideas and what we're seeing in the experiments. Okay. Now what about the horizontal surfaces? So these are different because the sine theta is 0. There's no component of gravity to drive these flows. However, they are driven by a hydrostatic pressure gradient. So we don't get fully developed states where things are only a function of distance off the boundary, but we get thin states where the flow depth is much smaller than their horizontal extent. And so we can use a shallow layer formulation, which essentially allows us to replace wherever we've had a sine theta, we can replace it with a dh dx. So our flux law becomes, we have this term which is linearly proportional to height, and a term which is proportional to sine theta, which then becomes dh by dx when we're looking over a horizontal surface. We're not quite there yet because I need to say how big is the slip velocity. In fact, I'm going to get to that after this, doing this. So then to complete the model for the horizontal surfaces, we then just balance the temporal variation of the height with the spatial variation of the flux. Now, what about the slip velocity? What I'm going to propose is that that is proportional to the driving force. And my way of understanding that is that what we're doing is we're misrepresenting the drag close to the boundary. So our drag term is developed for what's true in the interior, but of course near to the boundary you've got a slightly different balance as you're encountering a horizontal rigid planar surface rather than an ensemble of particles. Well, if you allow me to do this, our equation then takes essentially this form. So it becomes dh by dt is the spatial gradient of h plus some constant, dimensionless constant times h cubed times dh by dx. We want to solve this subject to constant flux, so the total volume is increasing linearly in time, and our front position is just to find where the height vanishes. Well, now, if A is very large, T would go like xf, the front position would go like time to the 3/5, a similarity solution. If A is very small, it would go like time to the 2/3. Experimentally, we were measuring that it goes like time to the 2/3, but these two numbers are pretty close to each other, so I'm not sure whether the experiments are sufficiently resolved to tell the difference between them. However, it is conceivable that this framework can account for the experimental observations. And of course, it's possible that both of these terms could contribute, in which case we would no longer have a similarity solution. So we'd expect a more complicated relationship between the front position and time, but it's going to be somewhere in between these two relationships. Okay, let me just say some words of conclusion here. So we've performed some experiments to look at gravitationally fluidized flow. And the point is that we've shown that you get a fully developed steady state. And we find a velocity profile which features this slip at the bottom and a shearing region over 10 to 15 particles. We then tried to develop a two-phase flow model of this motion, where the key feature is the drag between the phases. And we find that the motion, downslope motion, cannot be balanced unless we introduce some solid shear stress. Nothing else is big enough to balance the forces. And our experiments were at high Stokes number, and so we can anticipate collisions between particles. And then the interaction between the particles and the gas gives us this extra source of agitation, which then generates fluctuation energy. Okay, and of course, the real conclusion is that we need to do a little bit more work. Okay, so thanks very much.
Your equation for H, that's kind of a diffusive kinematic wave equation. If you looked at the tip of the gravity flow and how that looks like,
Yeah.
and the shear force there, is it integrably infinite or is it finite?
Sure.
How does it behave?
So, in fact, that was part of the point of those movies I showed, which didn't project so well. Where I slowed the flow down to 1 in 10 speed, and you can see the front coming through. And so it comes through with, it doesn't come through with a blunt front, it comes through with a finite gradient.
It is
or
regular.
It appears to be. Of
At
course.
the angle, does that come out in line with your A, for instance? You have to have?
Well, there are so many coefficients we don't know the flavor of that it would be hard to assess that. But it looks from the observation that there's a finite gradient at the front. However, the caveat is that, of course, at the front the flows are very thin. So maybe we need to be a little bit concerned about continuum approximations there in any case. But it does look as if it's finite gradient.
I have a problem with your dimensionless A.
Yes.
Because it means that H should be dimensionless as well.
Yeah.
And it's related to what?
Yeah. So essentially, I've scaled everything here. I'm not given the details.
No.
I've used flux and gravity, Q and G.
Okay.
Yeah.
Okay, let me give an alternative explanation of your solid force. People who do work in fluidization realize that minimum fluidization is something of a grossly average concept, and that locally the solid is not necessarily supported by the fluid at any given time. And I would suspect that it's something to do, for example, in your case, you have this thin layer, and you're going to develop channels that are easy for the gas to flow through and channels where it won't flow through. And those areas will be more of a granular flow than the other bits. And it seems to me that's a much more likely source of the your solid phase stresses. Just a comment.
Sure, and yeah, so we could close on that by looking at the fluctuations around the steady state. I mean, so essentially, when we look at these movies, we do see something which is fairly well maintained. We don't see big fluctuations, so it all depends
But
on
it
what would be
doesn't have to be big
what would be the
fluctuations.
time
We're
scale
talking
of
over a
the
couple of particles.
yes, but what would be the time scale of those fluctuations? That's the I accept the point that it could be due to the building of these intermittent building and then destruction of these force chains, but it would have to be over quite a rapid time scale. But that's possible; it could happen.
Final question, Jim.
Yeah, what's the relation between your closure and the increase in effective viscosity due to the volume fraction of the particles that Batchelor calculated, for example, or lots of other people have looked at?
I think I can't answer that in detail. Essentially, we don't really know the volume fraction very well. It's something we can't. We can take bulk measurements, but we can't take instantaneous measurements. So I don't think we have the data to answer that.
Okay, so we need to move on to the next speaker. So